Morning, CCN. Nice. Hope you all had a lot of fun at the museum yesterday. I thought that was a really cool spot for a social. So I'm really excited about this morning's session. We're going to hear some really cool work on language in biological networks and neural networks. I also wanted to give a plug for the diversity lunch that we're hosting today. It will be over in the sala over there, and we're going to have a community discussion about issues around diversity, equity, and inclusion, and how we can improve that in our field. So I hope to see many of you there. But it is my pleasure to kick off this morning's session. We're first going to hear from Diana Diemer from Western University. So welcome, Diana.
One second. Okay, there we are. Hi, everyone. It's so great to be here and kick this session off, and I'm so excited to talk about our work on action representations in the mind and brain. So our everyday visual experience includes a variety of dynamic events. We see people acting in many different ways, from different perspectives in different contexts. Yet we're able to quickly understand what they're doing, and we can quickly judge which actions belong together. We use this information about actions to make predictions, to infer social information, and to decide on our own course of action. Yet in vision, actions pose a particularly challenging problem because they act as a bridge between visual domains. Many studies of human actions have used control still images to investigate their neural mechanisms, which is great for isolating features and eliminating confounds. But in the real world, the actions we observe are much more complex, and we know that dynamic, natural stimuli engage our neural systems differently. However, natural stimuli also pose a very big complexity challenge because they vary along many axes that often co-vary with each other. So in any given action that we might see, we might need to extract information about agents, the tools and objects that they interact with, and the environment in which they act. So there's a lot of different axes to disentangle. And in this talk, I'd like to show you some work aimed at understanding how we make sense of other people's actions. And I'll focus on semantic representations, by which I mean the conceptual information that we extract in the course of understanding what other people are doing. And I'll first talk about the challenge of disentangling different types of information within natural actions. And then I'll focus on how this information is processed in the mind and in the brain by showing you some behavioral data, some EEG and fMRI data. So what do I actually mean when I talk about naturalistic actions? When we look at a video like this one, we can imagine defining the action it shows in several different ways. We might simply describe it using a verb, like swimming. And we know that verbs recruit dedicated neural circuits in the brain. But we can also say that this is an example of a sporting activity. And there is behavioral work that has shown that this might be a level at which we naturally think about actions. But we can also think about the motor goal of the action and say that this is an example of locomotion. And this idea is based on some primate research that tells us that actions that share motor goals are represented in distinct patches of the macaque parietal cortex. And finally, we can also think about what the action is directed towards, whether it's directed towards an object, a person, or the self. And this is another feature that we know is really important in organizing the neural representations of actions in the brain. So this is what I call our semantic features that I'm trying to disentangle in this work. And while we have reason to think that all of these may be important in action perception, they're very related to each other, and they can be difficult to disentangle. So to address this, we curated a specific data set that represents all of these categories at the different levels of abstraction, starting with a diverse set of action verbs, like boating or swimming, which can be grouped into common everyday activities like transportation or sports, and at a more abstract level into 8 action classes that represent the putative human motor repertoire based on motor goals, based on the primate research that I mentioned before, These are categories like locomotion, manipulation, ingestion, and so on. And finally, we can group all of these actions into 3 categories based on the target of actions. So whether an action is directed towards an object, a person, or the self. And to represent all of these diverse actions, we curated a set of 95 2-second videos of everyday actions from the moments in time dataset. And this is what I'll be using in all the work that I'm showing here. Because these are naturalistic and they vary along many more dimensions, we also annotated additional important features, including agent information and some perceptual information, including action features like the body parts involved in actions, the use of tools, as well as activations from different neural networks. I'm showing here just features from CorNet-S. And the main thing to take away from this correlation matrix is that our dataset does a good job of disentangling the semantic and social information from the perceptual information by keeping these correlations in this rectangle low. So next we asked, how do people categorize naturalistic actions? So at what level of abstraction do we think about actions when we're asked to categorize them? And to answer this question, we collected behavioral similarity judgments. So we asked participants to arrange the videos of actions according to their semantic similarity, so specifically focusing on the meaning of actions. And we used this data to generate representational dissimilarity matrices, which we then predicted using our feature set. And we used the cross-validated version of variance partitioning to assess how much unique and shared variance the different type of features explain in the behavioral data. And first, as a sanity check, we assessed whether semantic, perceptual, or social features better explain this semantic similarity judgment. And as expected, we do see in this Venn diagram here, we see that the semantic features explain most unique variance in the behavioral judgments. But there's also some contribution from perceptual features that people use in their judgments. And among the semantic features, we found that the target of actions best explain these judgments above and beyond many other fundamental features, including the class of actions. So it seems that when asked to categorize actions, participants do use the thing that the action is directed towards first and foremost to categorize actions. And next, we wanted to see how all of this information emerges in the mind, in the brain. So we collected some EEG and fMRI data to look at the spatiotemporal dynamics of action processing. And in an EEG study, we had participants watch these videos and perform a one-back task on actions. And then we used variance partitioning, but across time, to look at whether semantic information emerges in the EEG patterns. And before 200 milliseconds, we actually don't see much semantic information, like we'd expect. In fact, this portion of the EEG signal is well modeled by perceptual features. But after 200 milliseconds, we do see a significant contribution of the semantic features. And again, it's particularly the target of actions that best explains the EEG patterns and contributes the most unique variance, similarly to what we saw in the behavioral data. We also conducted a separate fMRI study in which participants watched the same videos and again performed the one-back task. And here we looked at how semantic features related to fMRI patterns. And we see most semantic and action representations in the lateral occipitotemporal cortex, just as has been shown in previous work. But the interesting thing here is that when we look at which of our features correlate most strongly using a searchlight approach, we see some differences. So in the posterior area of the lateral occipitotemporal cortex, the body parts involved in action are really important, while the anterior portion of this area appears to represent the target of actions. And finally, we use the EEG and fMRI fusion to better look at the spatiotemporal dynamics. And this means that we computed fMRI patterns from some regions of interest and then related them to the EEG data over time to get a better picture of what regions the signal that we're seeing might be coming from over time. And for looking at patterns from the early visual cortex and relating them to the EEG data, this is the correlation over time, and we can see that it begins to emerge at around 100 milliseconds. While if we do the same analysis for the lateral occipitotemporal cortex, we see a slightly later pattern, a correlation with the EEG patterns emerges at around 200 milliseconds. And we can look at this in a slightly more stringent way, again using variance partitioning to see, when in time each of the regions contributes uniquely to the EEG patterns. And here we see that indeed before 200 milliseconds, the early visual cortex contributes more unique variance, while after 200 milliseconds is the lateral occipital-temporal cortex that uniquely explains the EEG patterns. So together, we've seen, using behavioral EEG and fMRI data, that the target of actions is really crucial to our understanding of what other people are doing. So we've seen that people categorize actions according to their target in a behavioral task. We've seen that the target of actions explains EEG patterns after 200 milliseconds. And with fMRI, we've seen that this happens in the lateral occipital-temporal cortex. And together, these results show that socially relevant information, like whether an action is directed towards a person or an object, is crucial to human event understanding, above and beyond other fundamental semantic features that often covary and have not usually been disentangled. So this is all I had to say. I've got a poster later today, so if anybody's interested in more details, please come and visit. And I'd like to thank my labs and advisors. Thank you.
Thank you so much, Diana. We have time for one question while we're switching the laptops over. Okay, so yeah, you can come catch Diana in the coffee break to ask your questions. So let's give another thank you to Diana. So it's my pleasure to welcome our next speaker, Shelley Jane from the University of California, San Francisco. Give it away, Shelley.
Hi, everyone. I'm really excited to be here today to talk to all of you about our work on trying to understand the role of single neurons in the human speech cortex through artificial networks. So when you listen to speech, your brain has to extract all different types of information for you to be able to understand it, ranging from spectrotemporal modulations to modulations in the envelope and pitch, the phonetic content, as well as the context provided by the lexical information itself. But of course, speech perception is not this highly discretized process where your brain is extracting each of these different types of information instantaneously at a given time point. Instead, speech involves for the brain to actually integrate contextual information across many different time scales to represent all of these different types of features. So over the past decade, neuroscientists have found that local neural populations in one particular brain region, the superior temporal gyrus, actually represent information simultaneously and continuously at all of these different levels, but we don't really understand how. So in this particular project, we used high-density neuropixels probes inserted in awake human patients during brain surgery to try to investigate the role of single neurons during speech perception. Specifically, we wanted to know how single neurons are enabling the STG to actually simultaneously and continuously represent and integrate contextual information in speech to represent all of these different features. The data set that I'm going to be presenting today is from 17 different penetration sites collected from many different patients that span the course of STG. And we presented these patients with really simple English language sentences while recording the neural spiking activity. Now, traditionally, the way that we've tried to understand the role of both single neurons and populations in the SDG is by trying to fit simple linear models from the instantaneous representations of features in the speech input to the neural responses. So think of features like the instantaneous pitch of the sound or the instantaneous envelope magnitude. But this doesn't really tell us how the single neurons or the populations could be tracking contextual information. To answer that question, we used pre-trained speech DNNs like UBERT and Whisper that are actually able to integrate contextual information and represent information in the speech signal in a more continuous fashion. So we passed snippets of our speech stimulus along with some additional context into the pre-trained speech DNN, and then used the hidden states of the DNN to extract these more contextualized continuous representations of the speech stimulus. We then built really simple linear models to go from these hidden state representations to the neural spiking activity of every individual neuron. Through these deep neural network-based models of single STG neurons, we were then able to understand what types of information even single neurons are representing in speech. So just to show you how well these deep networks do, in this particular histogram, on the x-axis, I'm showing you the improvement in explained variance with these DNN-based features as compared to more traditional features that use instantaneous pitch or the instantaneous acoustic phonetic representation. And you find that overwhelmingly, over 82% of the neurons are much better predicted by these more continuous contextual DNN representations than traditional discretized representations of speech features. But there could be many things that are driving the performance of DNNs. It could be because the DNNs are highly nonlinear, because they're able to jointly represent information, or it could truly be because even at the level of single neurons in STG, we have contextual processing happening. So to investigate this, we leverage the ability of DNNs to very easily manipulate the amount of context they attend over. So we provided our DNNs with varying amounts of context, from 35 milliseconds all the way close to a second, and we evaluated how changing the amount of context over which our DNN captures information affects the ability to model a particular neuron. So now on the x-axis, I'm again showing you how well these DNNs do compared to traditional discretized speech features. But now on the y-axis, I'm breaking this down further to investigate how much adding longer context into the DNN enables modeling single neurons. And what we find is that there is this positive trend wherein neurons that are better predicted by the DNN are indeed benefiting from longer and longer amounts of context provided to the DNN, suggesting that perhaps the ability of DNNs to capture contextual information is what drives single neuron encoding. But this is not always true. In a different site in the STG, we find that there is this improvement with DNN that's uncorrelated with the ability to utilize context. And so what this tells us is that STG neurons actually show varying degrees of context sensitivity, from neurons that don't really care about contextual information at all to neurons that are integrating really long amounts of context and perhaps doing some feature integration. We can break down this result by looking at the context sensitivity of neurons that care about different types of features. So for example, neurons in light pink are tuned to phonetic content, while neurons in dark pink are tuned to pitch modulations. And you see that independent of the types of features these neurons tune for, they have a wide distribution of context sensitivity. So there are neurons that perhaps do feature detection in that they either care about phonetic content or pitch, but don't really care about context. In contrast, there are also features that care about phonetic content or pitch, but are very sensitive to long amounts of context, suggesting that maybe they're doing some types of feature integration that allows other neurons to represent phonetic features or pitch features. But there are many other sources of contextual information and compositionality in speech DNNs. We can not only vary the stimulus input itself, but we can also look at the different layers in these deep neural networks, because we know that deeper layers are able to compose information over longer spans of time. So we also evaluated how the neuronal encoding changes as a function of the layer from which we extract information in a speech DNN, and we found some pretty interesting results and a lot of heterogeneity. So now I'm going to show you the explained variance for every single neuron, but as a function of the layer from which we extracted features and the context length provided to the DNN, and we see many different encoding patterns. This particular neuron, for example, really benefits from adding more contextual information, suggesting that it cares about some longer range feature, but it's also slightly selective for deeper layers in the DNN, which have been shown to capture higher order things like phonetic information or word boundaries. In contrast, there are single neurons that don't really benefit from contextual information and are best predicted by the lower layers of a DNN that care about shallower features like spectrotemporal modulations. In the interest of time, I'm glossing over a lot of results and a lot of detail, so there's a lot more of this in my poster if you're interested, but these are just like some basic methods and results that we found. So given that there is this heterogeneity in both feature tuning and context sensitivity in the STG, I think the next interesting question is, what does this enable the population-level code to represent? Specifically, what does this heterogeneity in feature tuning and context sensitivity enable different local neural populations in the STG to represent in terms of feature representations? So what we did here is we tried to investigate if neurons that are sensitive to longer amounts of context are perhaps able to track speech information farther in the past. So we built this decoder and tried to analyze if the ability of a neural population that's long context sensitive emerges in the fact that it's able to actually decode information or decode spectral modulations that happened way in the past. Think about word level scales, so 300 milliseconds to 900 milliseconds in the past. Specifically, we split our neurons into two different groups. One group was context insensitive in that it didn't really care about contextual information, and another group was context sensitive, but everything else was counterbalanced between these groups. And we found that the context insensitive neurons very quickly degraded in their decoder performance from trying to decode something 300 milliseconds in the past all the way up to 900 milliseconds. But the context sensitive neurons were able to decode spectral content even 900 milliseconds in the past. And this kind of suggests that perhaps the feature heterogeneity and the context heterogeneity in the SDG allows local neural populations to track information at word level scales. So just as a quick summary, what we find is that single neurons in the SDG tune to speech features at very different context lengths that perhaps enables the SDG to rapidly integrate information at many different levels of the speech hierarchy. But the SDG, or non-human auditory cortex, is more sophisticated than just a set of feature detectors. So even at the level of single neurons, you see a lot of different types of feature tuning and a lot of context sensitivity. This is not just something that emerges at the population level. And lastly, we think that this heterogeneity is perhaps pointing towards more local circuit processing or more recurrent mechanisms that enable the SDG to simultaneously and continuously track information at so many different scales. So if you're interested in this work, please drop by at my poster at B128, and I'm happy to discuss more directions. Thank you.
Thank you so much. We have time for a question while we're swapping the computers. I'm going to ask a quick question to you tried a few different speech-to-text models. Did you find any difference between them?
Yes. Yeah, that's a good question. We actually find that better speech models lead to better encoding, which has also been established in the language neuroscience literature. But there are no principal differences in terms of certain deep networks doing better at encoding neurons. I think that points to the fact that a lot of these networks learn very similar types of representations, and hence maybe that's why we don't see any differences. Yeah.
Thank you. All right, let's thank Lily. Great. So now we have Katie O'Neill from Dartmouth College. Thank you.
Hi, as promised, I'm Katie, and we're going to talk about conversation and pink noise. So my big overarching question is, what makes conversation good? Now, every single word in this is underspecified, but we're going to go with it anyway. So there are many different ways that one could approach this kind of question. We could start with folk psychological constructs, things like respect and curiosity. We could focus in on specific conversational elements, like nodding and laughter. Or we could start with domain general cognitive mechanisms or patterns of mechanisms, things like foraging or reinforcement learning, and apply them to conversation. So today, I'm going to specifically talk about synchrony. So in the social cognition literature, synchrony is quite the hot topic, but it actually often functions as a folk theory rather than a set of mechanisms. So let's build some intuition here. We know that being out of sync with our conversational partner makes for bad conversation. So let's take a look at the world's worst first date. Person A says, I'm a huge baseball fan. Person 2 says, my dad never learned Spanish. Can we get a second dog? Art is dead. This is not going anywhere. But on the other hand, if we crank time-locked covariation in meaning all the way up to 100, we get something like this. I'm a huge baseball fan. I like baseball too, it's great. My son prefers basketball. My son also likes basketball more. This is really boring. Good conversation actually exists somewhere in the middle. So we might get, I'm a huge baseball fan, I like basketball better myself. Oh, so does my son, it's faster paced. Exactly, does your son play any sports? So what I want to know is, what is the mechanism behind what we colloquially call being in sync in this happy medium? And I'll argue today that this is mutual adaptation. So one thing that we can do is we can think about conversation as an interaction-dominant system. In dynamical systems, you can have a component-dominant system where each individual component additively contributes to the global outcome of the system. On the other hand, you might have an interaction-dominant system where the global state of the system is defined primarily by dynamic interaction. Now, this is not a perfect physical metaphor, but it is a useful visual metaphor. The one on the left, two independent pendulums, might be considered a component-dominant system because they're not interacting with each other. But on the right, we take the same pendulums, connect them with a spring, and they end up in places that they never would have been on their own. Now, a convenient fact of interaction-dominant systems is that they tend to exhibit pink noise. As a refresher, the color of noise comes from the relationship between log frequency and log power. So a scaling coefficient of 0 would give us white noise, this flat line here. If we have a slope of -2 in this domain, this would be red noise. And then we have this happy Goldilocks zone of pink noise. And this is what these signals might look like as a one-dimensional example. Very spiky white noise, very slow red noise, happy medium pink noise. As it turns out, pink noise is a hallmark of healthy coordination in things like coordinated finger tapping, heart rate variability, walking gait, even non-human signals like those in climate dynamics. So my question becomes, how can we quantify mutual adaptation in the semantic space of a conversation? Like so. So we're going to take each individual turn of a conversation when one person is speaking, and we're going to embed this in a 786-dimensional semantic space using MPNet. And this is this point right here. It might look like two-dimensional space, but you're going to squint really hard and say 786 in your head. So we'll do this for each consecutive turn in the conversation and create this overall trajectory of where these points are in relation to each other. Now, what you might notice in this conversation that I chose as an example is that these two people start very far away and then start to come in and talk about similar things. So what we can do is we can take the cosine distance between each consecutive embedded turn, and then we can do this for each conversation, each turn across the entire conversation, and come up with a continuous signal of what we call semantic similarity. Then we can use tools like detrended fluctuation analysis to find the noise coefficient, the color of noise of this signal. We're going to be applying this method to the Candor dataset, an open conversation dataset, where strangers have first conversations, having small talk like they've met at a party, and then they answer a series of surveys afterwards. So the first baseline question is, do we see pink noise in semantic similarity? And in these 1,600 conversations, the answer is yes. The grand majority of these conversations have a noise signature that falls healthily between white and pink. If you have questions about why they're so close to white noise, I have a lot of answers for you, but I only have 8 minutes up here, so we can talk about them later. But the next question we wanted to answer was, okay, is this actually a property of similarity dynamics, or have we just defined this semantic space in a funky way? So the way we can answer this is by taking each of these similarity trajectories, defining each of these points, and then creating a set of scrambled trajectories that we can then find the noise coefficients for. And if we do this 1,000 times for each conversation, we end up with a null distribution of what the noise coefficients would look like just with these set of similarities, not necessarily in the specific order that they came. And what we might find is something like this, where 50 of the scrambled conversations have pinkier noise than the original, while 950 have whiter noise. And this would get us a metric that we're calling pink noise robustness of 0.95. So are these pink noise signatures in the conversations actually due to the order in which people adapt to each other? And the answer is a resounding yes. These pink noise robustness scores end up far skewed towards 1. So it's one thing to say that there are these signatures of interaction-dominant systems in a conversation, but it's another to say that this actually means something. So I wanted to know, can we use pink noise robustness to predict conversation success? This is where this Candor dataset comes in very handy, because we have these 205 conversation variables that each participant answered. So we took 2 different approaches here. One was the exploratory, let's correlate pink noise robustness with everything. So after Bonferroni correction, PNR is significantly associated with these 12 variables here that seem to be strongly associated with positive conversations, things like enjoyment, self-disclosure, degree that the other person thought that we were friendly. Then another thing that we can do is we can post hoc sort these variables into factor-like groupings. So things like variables related to enjoyment, connection, engagement in memory, and then also demographics and low-level conversation features. So on this plot, each of these squares is each of these 205 variables. The color is what factor grouping it belongs to. Each star represents a variable that survived Bonferroni correction, and squares survived a more lenient FDR correction. And what we see is that there's a significant overrepresentation of variables related to enjoyment and connection in these variables associated with PNR. Also, if we take the first principal component of these different factors, we can get significant positive correlations with PNR for enjoyment and connection, but not any of these off-target variables. This leads me to believe that pink noise robustness is selectively associated with enjoyment and connection. You might have the question of, what if this is an artifact of XYZ thing? Come ask me about it at my poster. This is 8 minutes. I don't have the time. The main takeaway I want to give you is that conversation is an interaction-dominant system, so let's study it that way. Thank you to you for your attention, the people who give me money, and my awesome lab.
Thank you for that great talk. We have time for a question or two.
I think you're supposed to go to the mic, but I think I can hear you.
Okay. That's interesting. Speaking lab,
No, we're in the States.
But my question, actually, I am. My question is cultural difference, because in Finland, if the other person goes like, yeah, I know, I consider it rude, while in the United States, if the other person is silent, then that's actually rude. How do you consider cultural difference?
Yeah, I think there are pretty vast cultural differences. And I think that's actually going to be a property of the embedding space rather than the actual set of mutual adaptation. I think the baseline rules of the game are probably the same. It's just the way they're instantiated in different cultures varies. But I have no evidence for this. Who knows? I think that would be an interesting thing to look into.
I think we have time for one more question here.
Can you briefly say something about the time domain features that provide this pink, like the amplitude spectrum fall off that you're giving? It's typically a scaling law that you have behind that, and so you have things on a shorter scale, on a longer scale. Can you say something about that?
Yeah, so as you've kind of hit on, pink noise is a mixture of power in the high and low frequency domains. This is kind of an interesting kind of signal because it's not strictly temporal. It's on the basis of each individual conversational turn. Apologies, my hearing is not great, so I didn't entirely get your question, so I'm kind of just vamping based on what you've said. But yeah, I think there's something interesting going on there about kind of like longer scale trends in the conversation where you return to certain kinds of topics. You have this larger scale rhythmic activity that allows for a lot of flexibility in the short term. Why don't we chat afterwards when I can hear you properly? Does that sound good?
That's okay. Next
Awesome.
on your poster.
It's my pleasure to introduce Josephine Rogel from École Normale Supérieure. Take it away. Thank you.
Hi, everyone. Yes, I'm Josephine, and today I'd like to share with you some results about how the brain is able to maintain multiple words at once in memory, thanks to a dynamic neural code. So when you hear or when you read the sentence, "The quick brown fox jumps over the lazy dog," usually you don't picture all of these items independently, but it's more likely that you combine all of them together in order to get the full picture. So the maintaining and combining of these words is needed in order to make sense of a sentence. But how does the brain maintain all of these words in memory remains somehow unclear. So in order to tackle this question, we combined the data of several data sets in order to get more than 200 hours of humans reading or listening to stories while being recorded by magnetoencephalography, or MEG, which has, as many of you know, a high temporal resolution. And I will be presenting results of decoding and encoding, which both rely on linear regression. What I mean by decoding is the predicting of high-dimensional word embedding, words from the stories, and from the MEG activations, and encoding is the other way around, predicting of MEG activations from the word embeddings. So previous research has been done in this field. One of the established results is that even if a word takes on average 300 milliseconds to be said, it can be decoded in the brain for more than 4 seconds, so 15 times longer. So following this logic, it makes sense that we could decode many words at once in the human brain, as well as their respective order in the sentence that the human has heard. So for example, if I scale up this figure, we can see that we could decode up to 11 words above chance at once in the human brain. So for example, all the words constituting this sentence that we already saw. So we can decode multiple words in a long time period, but how does the brain actually maintain this information without mutual interference of the words? Probably through a dynamic neural code. And we're going to study this neural code now. So first, through encoding of the MEG channels, we can see that the patterns of encoding of a word evolves over time, from -2 seconds before the word onset, so there's anticipation, until more than 2 seconds after the word onset. First, there's a B activation in the parietal lobes, and then the information spreads out across the left hemisphere. So this dynamic pattern gives us a proxy for the dynamic of the actual neural representation of the word. This is the whole dynamic. And if we encode the five previously heard words in a different color here, we can already find encoding patterns of these words at 5 different processing stages. So we already get a somehow clear dynamic of the word's neural representation here. But in order to study even further this dynamic, let's move on to a more precise approach that uses contrastive decoding instead of encoding. So what we do is we fit a decoder on only one time step at 0 seconds here, this little cross. And then we use it to predict the word over the whole time window of the word processing. Then we fit a second decoder 400 milliseconds later, and we use it again to predict the word during the whole time window of the word processing. We can find that if we test the first decoder 400 milliseconds later, the time step it has been fit on, it performs already much lower than before. So this means that the neural code of this word is so dynamic, the neural representation of the word changes so quickly that 400 milliseconds later, the decoder can already not recognize the neural representation it was trained on, even if the encoding patterns still look somehow similar to us. And of course, the second decoder, which was fit on this time step, can perform just fine. So these are the two decoders here, one on top of each other. For example, in our running example, let's say that they were decoding the word jumps. So remember, we fit these decoders only on one time step and only on the current heard word. So here, the word heard at 0 seconds. So now, without any additional fitting, we can use these decoders in order to predict the previous words heard by the subject. So in our running example, we can predict the word fox, the word brown, quick, and the word even before, and we could go on. So these two decoders can decode all of these previous words without being fit on them, because the representations of these words follow a similar dynamic in the brain. We're going to look at this a little differently. So first, let's scale the scores. So we can see that the peaks of decoding follow the order of the words in the sentence. And now let's use the scores of decoder 1 as an x-axis and the scores of decoder 2, fit at 400 milliseconds, as a y-axis, in order to get a 2D projection of the neural code evolution during the processing of each word, like so. And now, if we plot the following words heard by the subject, we can see that they all follow the same dynamic, but in a sequential order, which corresponds to the order of the words in the sentence. So if we freeze the dynamic, for example, here at 500 milliseconds, we find that these two decoders can predict multiple words at once, simultaneously, at different stages of the neural dynamic, which corresponds to different stages of processing, and thus different patterns of brain activations that can be decoded. So in summary, the brain can keep accessible multiple words at once thanks to a dynamic neural code, dynamic neural representation of these words, which also maintains, of course, their relative order. So that way, for example, the fox jumps over the dog cannot be confused with the dog jumps over the fox. So if you're interested in chatting a bit further about this topic, or more generally inference in language, language processing in deep nets and humans, please come to my poster, B125, this afternoon. Thank you to my two PhD advisors and to all my lab mates, and thank you for your attention.
Hi, thanks for the nice talk. Speech is a stimulus that varies smoothly, and the brain, of course, has some smooth response to that. The extent of the smoothness is going to vary across regions. So it's a little hard for me to imagine how you could not see something like this. You know, there's going to be a sustained representation of words over time. The representation is going to evolve in the brain over time. So, yeah, I have a hard time seeing how something like this could not be the case, if that makes sense. Like if you imagined that, you know, there were different brain regions, they each maybe smoothed the signal by a little bit in different ways, I think that would give rise to like these types of effects, if that makes sense.
So then we agree?
But we know that. We know that there's nothing, like if you just took the speech signal and I smoothed it by different extents, we all think the brain is doing something more interesting than that, right? So I guess what new information does this tell us about the way words are represented in the brain? Do you see what I'm saying?
Well, first, for me, it's interesting to see, oh, sorry, it's too much. It's interesting to see which regions of the brain actually take the relay in the processing of these words. So I like to see this pattern of activation evolving in the brain. And also, of course, we know experimentally that when we process speech, we have to take into account the context and as many words as possible. It's one of the things that we talk about when we compare the deep nets with the humans. You know, the deep nets can take like so many thousands of words into context, and that's one of the main criticism. Like, okay, how do we actually compare such models to the human brain? Well, it's one first step. I like to see it as one first step to prove that we can actually take into account much more context than we thought, and this is proven now.
Okay, thanks.
There was really nice visualizations and interesting work, but following up on the logic of the previous question, if you have evoked responses in the system, you cannot but see what you see with the decoder. So the question is, how does the brain represent the sequence, regardless of, for example, segmentation faults, where, for example, you have no silence between the words? So I think that's where the previous question was going. So the understanding of the sentence has to do with being able to represent it regardless of its low-level features, you know? And segmentation of the words, regardless of, you know, pauses in between, is the kind of way to kind of maybe get at that.
So are you talking about the fact that we could, for example, take all of these items and then compress them into a higher order semantic representation of the sentence and the context?
Or just syntactic or phonological, but the point is that they have to be put into relationship regardless of the low-level features. And that's why I talk about the silence in between, because language, we tend to, even if there's no silence between the words, we tend to segment them.
Yes.
So if you're really decoding information that has to do with a word representation or a sentence representation, you would have to be able to get that order regardless of the low-level features that drive you to evoke responses, signals that are transient. You see?
So I understand several things in what you're saying. First, maybe you're asking about the fact whether we actually do decode the words, each word's embedding, and not just like, for example, the vector embedding that was related to the current word, because as you know, like many words share high-dimensional embeddings. And this, we have used like several encoding techniques that prove that it's actually each word embedding that we can decode. We can talk about it at my poster if you want. And then about the putting together of all the words in order to get the higher level concept of the sentence, and in order, for example, to store more information across time and a bigger context, it's something that I would like to work a bit more further into. And I think it's a very interesting question, but I would be glad to talk about it.
Thank you for the talk.
Thank you.
Thank you so much, Josephine. Okay, so now we have our final speaker of the session, Mo-Fan Lee from New York University.
So good morning, everyone. Seems my talk is a bit drifting away from the topic of this session, but if you're interested, I'm happy to share with you our neural network model that's trained on a vertical task, which learn multiple strategies of memory retrieval. So firstly, some basic knowledge. In the vertical task, you need to first remember a list of items, and then try to recall as many of them without any cue. So previous research has found various patterns in human vertical. And today, we will mainly focus on the phenomenon called the temporal contiguity effect. So human data shows that after recalling one of the items in the list, the next item will be most likely to be the next one in the original list that you study. So overall, people are more likely to recall items nearby the just recalled items, and are also likely to recall in the forward order. This is an important feature of episodic memory. So one of the widely known models for explaining the contiguity effect is the temporal context model. The model suggests a slowly drifting temporal context that retains information about previously studied items. And this context serves as a cue for memory recall. And the context for nearby items will be more similar to each other, so that this gives rise to the contiguity effect. And then based on TCN, prior work has shown that the optimal policy for free recall is to start from the beginning of the list and recall in the forward order. These optimal strategies match a memory technique known as the memory palace. So people who learn to use technique can imagine something like a palace in their mind and encode a list of items in some well-defined locations. And then they can recall the items by walking along a stereotypical path within that palace. So this strategy can significantly enhance people's ability to do a vertical task. So in this study, we trained a neural network model on the vertical task to study what strategy it learns just only by optimizing the performance. So the model was composed of a gated recurrent unit as the context module, and the memory module with a list of slots. And during encoding, the GRU receives a one-hot vector as an item at each time step. And for each input item, it will store its updated hidden state into the memory module as a memory. And then after encoding all of the items, we will reset the hidden states of the GRU and let the model start for recall. To retrieve a memory, the model computes the weighted sum of all the memories by their similarity to the current hidden state to form a retrieved memory. And this retrieved memory will be part of the input to the GRU. So we train the model with the advantage actor critic algorithm. It receives a reward for each correctly recalled item, and the recall order doesn't affect the cumulative reward. So this way, our training process does not bias the model to recall in a particular order. Instead, the model can choose like how to recall just to get a better performance. So, however, we found that our model actually learned a strong temporal contiguity effect after training. So, on average, the models are more likely to recall items nearby the just recalled item and also have a higher tendency to recall in the forward order. However, by looking at individual models with different random seeds, we found different levels of contiguity effect that's finally learned by the model. So, we then studied what could lead to this difference. Interestingly, we found that in a large group of the models, they actually learned the index code to recall always in the forward order. So here we show the first two pieces of the gyro hidden states during coding, and each trajectory here is a different trial with different presented item list. So we can see that the gyro hidden state actually followed very similar trajectories across trials, regardless of what specific items were presented in the input sequence. And then during recall, it can go through the same trajectory within the hidden space and collect each memories at a specific spot in the forward order. So we believe that this index code in the hidden space is very close to the memory palace technique. Meanwhile, some other models actually show a different strategy, and they encode less information about the item index, but rely more on the for example, the slowly changing item identity information, which could be different across trials. And we believe that this strategy is more similar to the TCN. So now that we have two groups of strategies, one is the memory palace that learns an item index code and always recall in the forward order, and the other is the TCM that mainly relies on the slowly drifting item-related temporal context. So to notice, when we decode each item, like item identity information from the hidden state, both these two strategies actually have gradually decaying item identity information. So you can understand that the models that uses the memory palace could also match the standard of the TCM. So therefore, we are using the decoding accuracy of item index information to quantify which strategy the model is closer to. So our questions are, what would influence the strategy learned by the model, and whether there is any advantage of learning the index code just as humans learn the memory palace? To better study these questions, we use two metrics to quantify the level of contiguity effect. So firstly is the forward symmetry, which quantifies the tendency to recall in the forward order, and then the temporal factor quantifying the tendency to recall an item close to the just recalled item. So the value of the two metrics of the four example models are shown below. So basically, the higher the value of these two metrics, the higher the level of contiguity effect you will have. So we then investigated how the task performance is related to the strategy. So considering a number of models with the same hyperparameter settings, we found that the forward symmetry is positively related to the vehicle performance. And this matches the human experimental data shown on the right plot. And the temporal factor is also positively related to the vehicle performance, which also matches the human data. And we also found that the better the model learns the index code, the better performance it will have. So this could roughly match to the fact that using the memory palace can improve the vehicle performance like in humans. And we then investigated the influencing factors of the strategy. So we found that one of them is the temporal discount factor during training. So the temporal discount factor modulates how much you add your future reward into the current time step when you're computing the loss during training. And we found that, so for the three metrics, we found that the higher the temporal discount factors, the overall higher level of contiguity effect, and also the more index code you will have. This means that so when you encourage the model to consider recalling the whole list at the beginning of the recall, the better it can learn the memory palace. So finally, here's a summary of this study. So in this study, we trained the neural network model with reinforcement learning to perform the vertical task and found human-like contiguity effect, even if our training algorithm does not bias any particular order. Our models showed individual difference in recall strategy, while some models learn the memory palace-like mechanism, some others rely more on an item identity-related temporal context. So this strategy could be modulated by some factors during training, such as the temporal discount factor. And we further found that learning the memory palace technique can improve task performance of the model, which is consistent with human data. So finally, thanks for my collaborators and mentors and also my lab members. If you want to know more about how we change between strategies and what are the like larger space of strategies, come to our poster at B162. Thanks.
We have time for questions. Okay, we can continue the discussion at Mofan's poster. So thank you all very much. Thanks for a great session.